The engine that goes on your rocket, that's a solid rocket motor, and this is a liquid rocket motor, so it's a little bit different. But using 3D printing technologies to make them as small as possible and leveraging all 3D printing technologies, because that's the new fame in propulsion engineering, because you can do so much with it, which I think you guys have probably seen. Can we go to the next, Robert? Here's some videos of, so in the middle is a photo of the first model rocket I built at Curtin. We started the Curtin Aerospace Club. So that uses like a, what size motors are you using, Robert?
C, I think.
C, yeah. So I think this was a G, which is quite a bit larger, or I don't know which way it goes.
Way larger.
Yeah, okay. So this one went to about 10,000 feet, or just above 3 kilometres. And that was about a 1-year project. We had a bunch of undergrad engineers at Curtin build it. We launched it, everything went well, and then we all graduated and the program kind of died. On the left is the video of our rocket. Are you able to play that, Robert? It's a bit pixelated, but you'll see how quick it goes up above the clouds.
All that work has gone that quickly.
Yeah. And the one on the right is another one that we built, which is kind of like a 2-stage rocket. It was much bigger, much slower acceleration. And I think that one went a little bit lower and something went wrong with it. But we would launch these out east of Perth somewhere with WARS, which is the West Australian Rocket Society. But yeah, it's exactly the same as what you guys are doing. It just used, like we actually built the nose cone out of fiberglass ourselves, so we didn't 3D print that, but we 3D printed the fins and all the other parts of the rocket. It had a parachute on board, a payload for getting the altitude. I think it had a barometer or some sort of pressure measurement device as well. It's literally exactly the same as what you guys are doing, it just used a bigger motor. And if you guys ever want to get into model rocketry, you can get your level 1 and level 2 certification, which allows you to launch rockets that are this big, because you need some sort of certification in order to do it.
And does WARS take members under 18?
Not sure. Yeah, I'm not sure. But yeah, pretty interesting stuff. So I guess I'd talk a little bit about 3D printing, because that's kind of what today is focused on. The whole goal is to turn a digital design that you do in computer software or CAD, and then turn that into a real product. And the middle step, which I think you're working on today, is you need to create an STL file. So I'm not sure if you all know how 3D printing works, but the 3D printing you're going to be doing is FDM, or fused deposition modelling, where you basically have a coil of plastic, has a little extruder, and it heats it up and melts it layer by layer onto a bed. And that's why we call it additive manufacturing, because you're adding to each layer. And in order to get from the computer to tell a machine to do that, you need to create an STL file, which will basically break up your geometry into those layers and tell the printer where to extrude the plastic. So it'll basically cut it up into each layer that the printer is going to print. Next one, please, Robert. So the main thing which you need to know for doing this is making sure your print orientation and overhang is correct. So if you're 3D printing a nose cone, like this one, like obviously this is a successful print, but you'll see the image on the left there, it says if the overhang angle is between 45 and 90 degrees, it will not print successfully. And that's what happens if you look at this T, the upside down T and the Y. The T on the left, there's a lot of errors going on because it just comes out at 90 degrees from the vertical. And 3D printers can't do this because they print layer by layer. There needs to be something below them to print on top of. And we call that overhang. You want to avoid overhang or your print inclination angle. And if you do, you can still come out at 90 degrees like that T, but you would need to add some support structures, which I've added in that very dodgy black line there. And
we showed you a little bit of that yesterday with Meg's Lego print.
So yeah, I'm not sure how if you guys know this or not yet, but yeah, this is like probably the most important thing when it comes to design for 3D printing. So if you guys become engineers or do manufacturing or anything like that, this is the most important thing when you design a part. Is generally you want to avoid support structures, so try not to have something that is past a 45-degree angle. This is a little miniature rocket thruster that I 3D printed, and you'll see, maybe I'll pass this around, you'll see these little tabs here. I have them coming off at 45 degrees. Do you want to have a look at that and pass it around? There's little tabs that come out the end of the rocket, and they come out at 45 degrees, so you don't have any supports. But if they were to come out like a T, I would have required supports. And when you're printing in plastic, that's not a big issue because plastic's cheap and you can remove supports easily. But if you start moving into printing metal and stuff like that, it becomes a lot more expensive to add supports because you can't just cut them away with a knife or your fingers. It becomes like an additional machining process. So yeah, with your nose cone, you'll see that this angle maybe goes to about 20 degrees, so it's totally fine. But if you change your nose cone shape and make it more stubby, like a, what's Blue Origin's rocket called? Their space tourism one. Yeah, neither. Anyway, you'll see some rockets, like they won't have a very pointy nose cone. It will be like snubbed at the top. So if you were to have it just flat at the top, you wouldn't be able to print that because you'd need supports under here. So try and keep your nose cone such that it never crosses the 45-degree angle and you won't need supports. Yeah, that's about it from me. Cool. Keen to see what you guys are up to. Who did I steal this from? You?